one.
Okay, guys. Take a look at these. How do you stabilize a cation? Move electrons towards it, pi electrons from the windshield wiper over. Put cation here, then lone pair from bromine can move in and make positive on bromine. That would actually be your major resonance structure. More bonds. That's it. 2 resonance structures. How we do? You do not want to use the pi bond here, because if it comes over here, you'll leave the oxygen with no lock tip. You don't want to do this. That would not be better. That would not be more favorable than the one shown. That would be worse than the one shown. That one's the best of them all. This one's better than the one shown because here the cation's more substituted with the additional methyl. The anion, how do you stabilize the anion? Move electrons away, electrons in, electrons out. We can get to this, electrons in, electrons out. We can get to that, which would be the major with the minus on oxygen.
Could you move the lone pair, the extra lone pair of the nitrogen to the other sigma bond and just have one major?
You mentioned sigma bond.
Well, the nitrogen has 2 sigma bonds on it, right? One of them's connecting into the hexane ring. The other one, the one to its left, the bond.
What do you mean, here?
Yes.
And do
just
what?
have a pi bond over there.
A double bond here?
Yes.
So this carbon, you would have how many bonds to it?
2 bonds. Just have a pi bond over there.
Well, there's 3 H's bonded to that carbon. You want to make 5 bonds to carbon?
No.
You were looking to win Nobel Prize? Carbon doesn't make 5 bonds. You said sigma bond. One of the golden rules of resonance is don't go messing with sigma electrons. But you were making a pi bond anyway. No, you can't make a pi bond over there. You'd have 5 bonds to carbon. That's it. D major. Most stable. Well, we're doing HCl, heat. We're going to get cations shown over there, here, and then here. Cation is going to add to, the chlorine is going to add right here to give this product, which is the most stable that you can get from those 2 cations. How we do on that one? Questions about that one? First one is the product. How we do, Dan? What happened?
I just moved the bond around.
How we do? Asia?
Can you explain that again, how that's the most stable?
How this is the most stable? Because, compared to which one? Compared, compared to this one? Coming from this cation? If chlorine attacks here, you get this. Right? Right? Which is more stable? Double bond conjugated with benzene ring, more conjugation, or double bond not conjugated with benzene ring? Conjugation is better, right?
What about the fourth?
Well, the fourth one would not, the second, the third and fourth would be no good at all because this is the best cation. This cation is here and here. You look at the cations. If instead we put cation here, H plus here, to give new H here, cation here, resonance stabilized, then we can show resonance put cation here. That's secondary, and this is secondary. Okay, but over here, what do you have? Secondary, and what is this?
Secondary.
Yeah, but what else is it? This is a benzene ring. It's resonance stabilized. That's secondary with resonance. Which is better, secondary, secondary, or secondary, secondary, one of them is resonance? Additional resonance. Additional resonance. Yeah? So once you see that this is the best cation, then you get rid of this, and you say if the chlorine adds here, you get the first product. If it adds there, you get the second product. Heat gives most stable. Which is most stable? Double bond is disubstituted in both. You got to look for something else. Well, here the double bond is conjugated with the benzene ring. There it's not. Conjugation is better.
So we don't have to look at the cation formed from the double bond on the right, because one would give a barrier.
And the double bond over here.
So if we moved, starting from the beginning, if we started with the H attacking the double bond on the right.
Which is what we did here.
Okay.
And then resonance gives this. This cation is better than that cation. So we forgot about it. With heat, you get the most stable product. Is the most stable product going to be the one where chlorine adds there or there? There or there? Here. The double bond is conjugated with ring. Question?
But chlorine, the way I said it, chlorine also has lone pairs, right? So wouldn't it be beneficial for the lone pairs of chlorine to be closer to the ring too?
Okay. Here? Why would it be beneficial for the lone pairs to be closer to the ring?
Okay, I see now.
There's no p orbital here, so the lone pairs are not conjugated with the ring. Is it better to have double bond? What if this was just an alkene over here? Would it be better for the double bond to be conjugated with that double bond or not conjugated? Well, hopefully you would say conjugated, because if we go back to the resonance outline, the first thing we looked at was conjugated diene is more stable than a non-conjugated diene. This guy here, lone pair in, electrons out, put minus here. This has partial minus of this carbon. This has partial plus here. You want to make sure this bond's here. You want to flip this over. Basically, this is the product. About this alkene, the groups are trans, so they're going to be trans here. You're going to get this product plus enantiomer. Questions about that one? Pretty much just like the one or two we did for Diels-Alder. There's a variety of cleavage peaks you could get here. Alpha cleavage next to carbonyl could give this cation. Alpha cleavage with the ether could give this cation. Both of these are on atoms next to lone pairs. Atom next to lone pair. There's a couple other cleavage sites that are possible as well. This will be posted. How do we do?
So on the last one, if the lone pair from oxygen were to go towards that cation, that would be rearranged, right? Would that be the collaboration?
No, that would be resonance. Here, this is resonance.
What did you say?
Flatly is a rearrangement.
With the hydrogen.
Yeah, you start moving atoms. We're not moving any atoms here, we're doing resonance. All we're doing is moving pi electrons. Okay, substitution reactions. Right here, right here. Let's consider these two. You can't see the green, just yellow back there. These two here. Which one would be more reactive in a SN2 reaction? That one or this one? Which one would be more reactive?
Bottom. Just depending.
Why this? All these would be more reactive than that. That's what I got right here. I just have one less carbon. Why are all these more reactive than this in an SN2 reaction? Because next to the carbon that's being attacked, right there, we have inversion here. What's next door? P orbital. P orbital. When you have a P orbital next door, what does that do to the transition state? Stabilizes it. P orbital overlap. The carbon, this carbon becomes sp2-like. In the transition state, overlap the P orbital stabilizes that. All these here are very reactive in substitution reactions. They're actually very toxic because they'll do substitution reactions with the nucleophiles in your body, like DNA or proteins. Proteins in your eyes. This compound's going to be less reactive towards SN2. There's no P orbital next door. So you don't get that stabilization. Less reactive. Substitution here is going to require probably heat, longer time. This is going to happen at room temperature, almost instantaneous. That's the difference with that stabilization. This is called ethyl chloride, or 1-chloroethane. Ethyl chloride. Anybody ever heard of ethyl chloride? Anybody play baseball, watch Major League Baseball? Ethyl chloride, what do they use it for?
Or is it sticky on your hands?
No, not fine tar. If somebody fouls a foul ball off their ankle, the trainer comes out and sprays something on them.
It's like a numbing.
What do they spray on them?
It's like a numbing.
Ethyl chloride. Yes. It numbs it. It makes it cold. So this is a gas, but they have it compressed. And when they spray it out, it's a liquid. But as soon as it hits the warm skin, it evaporates. To evaporate requires heat. If you remove heat from the surroundings, you make the surroundings cold. They use this to make the air go cold and numb it. They would never spray this on somebody. This would be considered a tear gas. This would be considered a toxic agent. Much more reactive. This is less reactive and it can be used for that purpose. Okay? If you watch the Braves back in 1996, I don't even know if y'all were alive back then. Tim McCarver said, oh, they're spraying ethyl chloride on him. He said it was ethyl chloride. Apparently never had organic chemistry. Ethyl chloride. Okay. What are we looking at here? We're under E. You guys do look at the headings, right? We're looking at the reactivity of various electrophiles. The electrophile contains the leaving group. Okay? We looked at these electrophiles versus maybe ethyl chloride and how we can have difference in reactivity. Let's look at something else. Let's look at the effect of carbon substitution on the reaction rate. Look at all these compounds. They all have a bromine leaving group. So the leaving group is the same. On methyl, on a primary carbon, on a secondary carbon, on a tertiary carbon. This is called a primary halide, secondary, tertiary halide. The rate, methyl bromide is much faster. What's your favorite nucleophile? Let's just say DNA with an amino group. This will attack this carbon and kick off that bromine in an SN2. What type of reaction are we doing? SN2. Not SN1, right? This is much faster. If this tried to attack here, why is this slower? Well, it's slower because of steric crowding or congestion. Remember, there's H's here. They're small, but they're there. You can't get to the carbon because of all these atoms here. It blocks it. That's called steric congestion, or just sterics. the atoms block and the nucleophile cannot get to that carbon backside. If we draw this out here, you see these H's are fairly small. And this can just squeeze in here. Kick that off. But over here, all these groups there, it makes it sterically crowded. It slows down the rate. And here's the take-home. This is going to be faster than this. That's going to be faster than that. This is much faster than the tertiary. In fact, you never do SN2 with a tertiary halide. It's like, okay, if you're going to be organic chemist, you got to repeat after me. Never do SN2 with a tertiary halide. Say it again.
Never do SN2 with a tertiary halide.
Right. Now, of course, I know every semester somebody does it. I don't know why. Don't do it. Too sterically congested. It's like trying to pull a jumbo jet into a little tiny hangar for over on Daniel Field. It just won't fit in there. Okay? Sterics negatively affect the rate of an SN2 reaction. Note, the above trend is just the opposite for an SN1 reaction. Which reacts faster with an SN1? Tertiary. Why? Because the rate determining step is forming a carbocation. Which one of these is going to form a carbocation the fastest? Tertiary. The trend is just the opposite for SN1. But you knew that already. Now, methyl bromide is actually very reactive in SN2. Not because there's a p orbital next door, but because there's no steric congestion. Methyl bromide is a gas that's used to fumigate warehouses to kill roaches and rats and all types of stuff like that. It's very reactive. So this guy is just as toxic as those, but for a different reason. Okay, look at examples. Here's an example, continuing the same idea. Here's a reaction with carbon group and bromine. We're replacing the bromine with an iodine. Can you do that? Yes. The iodine is a nucleophile. It replaces the Br. Lithium iodide can be the iodide source. Shows the rates here. We have methyl, primary, secondary, tertiary, shown here. The rate for the methyl is 163. That's relative compared to primary being 1. So you see the methyl is 163 times faster. 1. When we go to secondary, it gets slower compared to 1. And when you get to tertiary, it's negligible. Or basically for us, we say you don't do it with tertiary. So there's some actual data. Okay, next idea. Again, we're looking at the substrate with the leaving group, the electrophile. What about the actual leaving group? We've already said that iodine is your best leaving group, bromine, chlorine, and that's much better than fluorine. Basically, the larger halogen is your better leaving group. For example, these two substrates are the same. They're both primary, but we have a different leaving group. Here the nucleophile is what? Well, this is O minus K plus. Forget about the K plus. This is O minus. It's your nucleophile. This will attack here, kick off the iodine, and we can get the new bond to the carbon, kick off the iodine. Show the potassium there. That's a pretty easy reaction with iodine. If you try to do it with fluorine, it's very difficult to impossible. So we first say that obviously the iodine is a better leaving group. Because the reaction is easier. It's easier to substitute an iodine. Much more difficult to substitute fluorine. Almost impossible. Fluorine is not a great leaving group for SN2. Now, why is iodine a better leaving group? Well, let's look over here at the stability. Up here we're making I minus, and here we're making F minus. Which is more stable? Which is more stable?
Yeah,
I minus, why?
it's bigger.
Because it's larger. The charge is more spread out over a larger atom. Yes? Which is more acidic, HI or HF? HI, because where is it going? Where is this going? I minus is more willing to form. Stronger acid. I minus more willing to form. Here, I minus more willing to form. Now, what is counterintuitive here? What's a different argument? Somebody could say, well, hold on. Isn't there more partial plus on that carbon? Indeed, which one? Which carbon has more partial plus? One with the fluorine. So wouldn't that make the O minus more attractive there? Perhaps it does. But the results tell us that the reaction is easier up here. So this is a counter argument. That's the wrong argument, apparently. There's other discussion we could have here. I don't want to go into it too much more. In the end, iodine's your better leaving group for the halogens. Now in practice, usually bromine is used more often because a couple of reasons. Iodo compounds tend to be more expensive. Iodo compounds tend to be less stable. In practice, you see bromine used more often. Actually, you sometimes see chlorine used even more often because chlorine is the cheapest of the halogens. In industry, they tend to use chloro because it's the cheapest. They're using 100 kilograms. But they're using they're not the greatest leaving group. In terms of price, stability, and everything, bromine is usually the most used, especially at the research level. Iodine is just more expensive and less stable. So just a couple of practical considerations. Okay, other than halogens, what other atoms can be leaving groups? Well, oxygen can be, but we have to activate it somehow. For example, if we do the same reaction up here but have like an OH and say, okay, could this come in here and kick off the OH, replace the OH with an O-methyl? No. No reaction. But if this was an iodide, bromine, or chlorine, it would work. OH will not act as a leaving group or as an LG in a slow rate determining step. Now I could say in SN2, hydroxide will not act as a leaving group in SN2. This is just a broader statement. We know in SN2 the leaving group leaves in the rate determining step. And see, there's other mechanisms, and in other mechanisms this broader statement applies to other ones. So how can we get the OH to leave? Can we? We actually can. One way to do it is by protonating it. This is an additional step in the overall mechanism. It's an activation step. If you take the same alcohol, we can get the product by doing it this way. Instead of methoxide, just use methanol and an H+ catalyst. protonate the OH, we can get it to be a leaving group. Let's show that mechanism. The first thing is the lone pair reacts with the H plus catalyst. And we get a protonated OH that looks like that. Now this H plus is coming from a strong acid. Takes a strong acid to protonated OH. What's your favorite strong acid, AJ? HCl. Okay, I wouldn't use HCl here. We've got to be careful. Most commonly it would probably be sulfuric. This may be written down below. I'm not going to spell it out here. I'm pretty sure it's spelled out below. We'll see a problem with HCl. Protonated with a strong acid. Now this will be your Lg. That's not OH. It's not, hydroxide is not going to leave. We're not going to make hydroxide when that leaves. When this leaves, what are we going to make? We're going to make water. Hydroxide won't leave as in a rate determining step, but water will leave. Protonated, then the nucleophile. How do you recognize a nucleophile?
Negative charge.
Not always a negative. It has a lone pair. Could be neutral. Has a lone pair. See, here it's neutral. There it was minus. These electrons will now come in, attack carbon, and kick that off. Kick off the leaving group. And an SN2 concerted backside attack. What does that give? Not product yet. We get boom, boom. Now bonded to that is the oxygen with the methyl, but that H is there. And that's a plus charge, plus what? What left? Water. There's the water with two lone pairs. And lost that H. Now where did we lose it? How do we get rid of it to get final product? Something has to take it. We got H SO4 minus that can take it. It's okay not to show full Lewis structure here. Take the H, these stay behind. We make that. What do we reform? We reform our acid catalyst. We made the OH a better leaving group by doing what to it? Protonating it. It was a step before. This is your rate determining step. The actual kicking off the leaving group. This is an activation step. How many intermediates in this mechanism that we showed? 2. It's protonated OH, and then we protonated here. 2 intermediates. Transition state leading to that, transition state leading to this, transition state leading to that. For some reason, you guys tend to think that an SN2 is always one step. Well, the replacement of the leaving group is one step. This has an activation step to it, and a removing the proton, okay? The one-step part is the replacing the leaving group. That's one step. Why not do this reaction like this? The same here, H+, but use the stronger nucleophile. We'll talk about nucleophile strength. Indeed, O- is stronger nucleophile. Why not do it like this? Why is there no reaction here? Why did I have to use the neutral nucleophile? Why can't I use the minus? Because you cannot have acid and base in the same reaction. H plus and O minus in the same reaction? No. What will you get if you mix these two together? The O minus will react with the H plus and you'll just make methanol. Well, that's okay, but you're going to destroy your H plus. H plus can't exist in the presence of sodium hydroxide or sodium methoxide. Let's boil it down to something simple. When you're taking a bath and you turn on hot water and cold water and they go into the tub, what is the temperature of the water that you get? Warm. Hot and cold are going to neutralize each other and you're going to get warm. Acid base is going to neutralize each other. You can't fill up a tub with hot and cold water and then say, okay, I'm going to use the hot water in the tub. There's no longer hot water in the tub, it's just warm now. You can't have your cake and eat it too. If you're going to use H plus catalyst, you've got to use a neutral nucleophile that won't react with the H plus. Okay. Down below, we can see a variation of this reaction that works very nicely. Very bottom. If you take that alcohol reacting with HI, you can get a reaction and get an alkyl iodide. First off, is this a good leaving group? No. How do you make this a better leaving group? The first way. Protonated. Got to have an H plus. Is this a source of H plus? Yes, HI is a strong acid. So this is H plus. What else is this molecule a source of? It's also a source of I minus. I'm going to just protonate this without drawing the mechanistic step. You see how we can protonate this with the H plus? Then the I minus can come in, kick off that. What do you get? You get that plus water. A very common reaction is to take an alcohol with HX and to make an alkyl halide. Got the H plus there, you got the nucleophile there. Up here we had to have H plus and nucleophile separately. Note, in addition to OH groups, OR groups can also be leaving groups if protonated. Predict product here. Now when I say predict product, it's kind of like in math if I said, okay, give me the answer. How would you get the answer? You would usually work an equation. What's the analogous working here? Mechanism. Using mechanism, think through it mechanistically, propose product here. Let's see, I've got this ether with HBr. First off, in organic 1, we don't do any chemistry with aromatic rings. There is pi bonds there, but we never react them with H plus in organic 1. They're not typical alkenes. So forget about benzene ring in organic 1. All we really have here is this oxygen. What can you do with that oxygen with HBr? Protonate it. Now you can show the mechanistic step, or you can just, if you know how to do that, let's just protonate it. Does everybody agree we can protonate it? HBr is a strong enough acid to protonate. Okay? We got that. What else is in the mix? Br minus. What can that do? What did the heading say? In addition to OH, OR groups can also leave. OR. So the oxygen and an R group are going to leave. Okay, finish it up. Mark.
Can you do resonance also for this one stabilize the plus charge?
No, there's no resonance here.
With the ring?
What do you want to do? Put
Yeah.
electrons there? Well, let's look what you would get. You would get Double bond to oxygen, yeah.
Yeah.
With an R group and an H and a lone pair. I mean, the lone pair didn't just disappear, did it? How many electrons you got around oxygen? 10. Nobel Prize. Okay? This oxygen does not have a p orbital. No, it actually does, but you can't move electrons that way. You can't have 10 electrons. What's the product here? Get rid of that. In this case, we have two different carbons. The oxygen is bonded to two different carbons. Over here, oxygen was only bonded to this carbon. We attacked this carbon, kicked off the oxygen. In this example, the oxygen is bonded to two carbons, here and here. Which one are we going to attack and kick the oxygen off of? Left or right?
Right.
Right.
These electrons attack here, kick that off. What do we get? That plus that. The leaving group was the whole thing in the box. What did it leave? It left that carbon right there. Bromine is now attached to that carbon. We get that over there. This was your leaving group. If under my hand was an H, that would have been water that left. Instead, it's an R group. So it's an OR that left. OR groups can also leave. Why didn't we attack the carbon on the right, not the one on the left? We could theoretically attack here and kick the oxygen off of that carbon. Well, to answer that, I would ask you to go back to the very beginning and look at the heading. We do this at what type of carbon? Tetrahedral carbon. Which one is tetrahedral, right or left? Right. That's a trigonal planar. You don't do SN2 at a trigonal planar carbon.
That's tertiary.
It's not really tertiary. It's not a saturated carbon, so we don't really call it primary, secondary, tertiary. It's a trigonal planar carbon. It's sp2, trigonal planar. You don't do SN2 there. Don't do it. Let's see. You don't do SN2 at a tertiary carbon. You don't do SN2 at an sp2 trigonal planar carbon. How did that reaction look otherwise? Protonate, Br attacks, kicked it off. That was the leaving group. It's the same chemistry. Now later on, we can maybe call this an ether cleavage reaction. Because this was an ether, we cleaved the group, and now it's a phenol. I mean, you can step back and say, okay, what did we do? But mechanistically, it should be pretty straightforward. Another way to make an OH a good leaving group is convert it to a tosylate. We'll look at this next time. Please look ahead in this handout. We're going to move through this quickly. I would expect that you have looked ahead, made questions, be reading the chapter. Okay, guys, see you soon.
Dude, it's good, right?
First chance?
Oh, yeah, the first two is
Yeah, like, wow.
Yeah. But they're actually like a new season, like based off like a prequel to it or something else.